So it's great to be back, and it's always fun. This is the 7th summer school, and it's the 6th that I'm teaching it. And looking at the title slide, the names of people that I think keeps increasing every year because they keep adding new material that has been published in the last few years. And at this point, there's a lot of material, and I used to go very deep in specific parts and then more shallow in others. But in order to cover everything, we have to squeeze things a little bit. So I'll go over the basic algorithms in detail, but then I'll try to cover more recent work at a more high level because we don't have time to go into everything. But depending on what Chris Dyer teaches tomorrow, a lot of things should hopefully connect nicely. I haven't seen his slides, but some of the newer things with recurrent networks, I will glance over, and then tomorrow you'll get a more in-depth view. So before we jump in, just so that I understand a little bit who I'm talking to, how many of you have primarily a computer science background? Okay. Any linguists? Okay, smaller number. Used to be more in the past. And I guess everybody's interested in machine learning. How many of you know something about syntactic parsing already? Okay, well, why are you here? So actually, I forgot to update the title on this slide. On the web page, I said I don't want it to be just syntax. I want it to be more broadly parsing. And I thought I would start with one sort of slide talking about why do we care? And I think that, at least for me, there are two reasons why I care about parsing. I want to take unstructured text, raw text sentences, and review the structure of it. And this can be syntactic, so grammatical, or it can be semantic, or it can be grounded in something else, like an API where you make function calls, and if you talk to your assistant, you expect it to execute some command or evoke some functionality on your phone. And you need to go from text to these functional representations. And a lot of the same algorithms can be used for these types of problems. But in order to evaluate on something that is commonly agreed on as ground truth, there has been a lot of work on syntactic parsing. I think sometimes up to the point where people got carried away and forgot why they're doing it in the first place and just blindly optimize an accuracy metric rather than trying to use these structures. But I think because there's good evaluation data, people have been working on it. And then the algorithms that are being developed, either the grammatical output itself can be used in downstream applications because we believe from our linguistic intuitions that grammar is important for meaning. And I'll try to make a pitch for that. But the other reason why this field is important is that these algorithms can then be taken and trained on different data, and they can produce generally tree-structured output, and so you can frame a lot of problems this way. So structured prediction, as you saw already yesterday with Xavier, is important, and tree structures in particular can be very useful. So here's my attempt of connecting syntax to meaning, and if I give you the sentence, they solve the problem with statistics, you'll have probably one interpretation in mind right away. Presumably that statistics are being used to solve some problem. And that would correspond to this interpretation where we bracket solve the problem as one unit, the stronger affinities between the verb and the problems. And then statistics as a prepositional phrase is used to describe how the solving is happening. But there is an alternative interpretation where we say the problem with statistics And so you can think about it in some context of a homework, or the problem with the broken car, that type of interpretation. And it's being solved, and you don't know by what means. So if we can understand the grammar of the sentence, the hope is that we can get closer to representing the meaning. Whether this is true, I'll leave out there. But we have seen a bunch of applications in different domains. Translation used to be one of the cases where syntactic analysis was very helpful. Now with neural machine translation, maybe it's a little bit less clear. Though even nowadays, for languages with small amounts of training data, you actually still do better with a syntax-based phrase linear system rather than with a neural system. And so in question answering applications, it can be useful to be able to parse and understand the question. It can be useful for extracting potential answers that are grammatical, and so on and so forth. But I'll conclude the second part before lunch with some examples of tasks that used to traditionally rely on syntax, but nowadays we can bypass syntax and go directly to the higher level output. And so I think there's an open question of what role syntax will play going forward. But in the meantime, I can assure you it's being used in a bunch of places. We parse every query as it comes into Google, and we parse every document as we crawl it, and we store the information and make it available to the product teams that then try to use it in the products. But when you can train end-to-end on a lot of data, the role becomes perhaps different. So we're not going to stop at bracketing, but we will produce these hierarchical structures where we form minimal units and then combine them to larger units to get this parse tree, and we'll give it labels. So we won't call it just X, but we'll give these things names, like each word will have a part of speech tag, pronoun, verb. I'm simplifying here. The problem is a noun phrase, prepositional phrase, verb phrase, and so on and so forth. And the different structures will correspond to different parse trees. So this is the first interpretation that we looked at, where the problem and solved are being combined first, and statistics are being used to solve them. And this is the other one. Now, constituency parsing is what is typically used for English, or if people work on constituency parsing, they typically work on English. Let's put it this way. In the last 5 years or so, I would say dependency parsing has become actually the more widely used formalism. And the corresponding dependency parse tree would look like this, where we have arcs between the words that indicate which word modifies which other. And we can express the same distinction as in the constituency parse tree here by moving the arc that connects the prepositional phrase, basically the head of the word, with whether it goes to solved or the problem. Now, so that I don't lecture the whole time, but we have a bit more of a conversation, do you think the two formalisms are equivalent? Can you express everything in a constituency tree that you can express in a dependency tree, and vice versa? Anybody take a guess, or do you want to vote? Anybody? Yes? Yeah, so constituency tree, because it's a nested structure. If you want to have an arbitrary connection between words, you have to put them into the same constituent, so crossing brackets is not possible. And so for free word order languages, or languages where you have verb movement, they might not give you the flexibility that you want, so then people try to do some secondary structures on top of that, but it becomes quickly cumbersome. The other way around, are there things that can be expressed in constituency trees that cannot be expressed with dependencies? or are dependencies strictly more general?
Can you add a hierarchical structure?
The question is about hierarchical structures. And so one simple example is if you have in a constituency tree, you can have unary rewrites. You can have just something being a pronoun, and then it functions like a noun phrase, as we saw on the previous slide. And you can make it look a little bit like that in the dependency tree by expressing the hierarchy in the label. But it becomes messy. Other thoughts, questions? So in general, they are kind of like you can show strict properties, and there's a nice paper by Owen Rambo that compares exactly what type of representations are covered. You can put a lot of information into the labels if you want to preserve it, but typically there will be things that are more naturally expressed in one, and like the crossing arcs, hierarchical structures are better expressed in constituency trees. They're easier to read, and when you go from one representation to the other, oftentimes you'll have a lossy process. So for the English tree banks, as the corpora are called, which contain these labeled examples from which we train, the linguists in the 80s and actually early 90s annotated constituency trees, and we have deterministic converters that will take the constituency tree and convert it to dependency trees. And they preserve most of the information, but not all of it. For a lot of the newer tree banks, the annotations were done directly in dependency formalisms, and converting to constituency trees is rarely done. And so there are different schools of thought, and depending on what you might want to do afterwards, one representation might be better than the other. But overall, I would say dependency parsers are nowadays more popular because there's more data available for more languages. They're more flexible to capture the phenomena in many languages. Thanks to this universal dependency tree project, we have corpora in the same annotation standard. So the labels are the same across languages, which is very useful in a practical setting. And then last but not least, an important argument for dependency parsers is that the parsing algorithms tend to be faster and more efficient. So if you want to process lots of data, that can be very beneficial. Real sentences, of course, are a lot more complex than what I showed before. So this is the first sentence of the development set of the Penn Treebank. And if I were to ask you to parse this sentence, influential members of the House Ways and Means Committee introduced legislation that would restrict how the new blah, 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 blah. You'll probably have to take a deep breath first and look at it closely. And I don't know what strategy you would use, but you might start with the simple units and then kind of build them up to larger structures. And we'll keep that intuition and see how the algorithms actually do this bottom-up and top-down. So as I said, we can convert between the formalisms. And here are some examples of why getting beyond bag of words representation is important. If you just have a bag of words representation, all of these sentences would look very similar in terms of what you can model, but the meaning tends to be different. And so one question that often arises is, are bigrams or n-grams enough, or do you need tree structures? And of course, if you're thinking more about the linguistics and the phenomena that occur in language, you certainly need tree structures. It's not that hard to show examples where n-grams are not going to be enough. But in practice, it might actually be that bigrams capture 80% of the cases, because you don't need to parse from I cleaned the dishes from dinner. Like, it's very clear, like, if you have the unit from dinner, what that means. But how to build systems that can rely on simple n-gram representations most of the time, but once in a while bring in more structure, is, I think, an open and interesting question. So now let's look at how parsing might work in more detail. Here's a simple sentence that raises interest rates by 0.5%, actually quite timely. And we will first start by assigning part-of-speech tags, and given a small lexicon of that just tells us for each string what are potential part-of-speech tags that we have seen in a corpus. Here are a few of the possibilities, and then a simple grammar that tells us, okay, how can we put these things together? Already kind of creates a lot of ambiguity and a lot of possibilities of putting these things together. Even though there's only one obvious interpretation, you get this combinatorial explosion. And the goal of parsing is to find the needle in the haystack, because there's going to be only one correct interpretation, but there are many, many possible ones, and we want to adjust the set of rules that we have and the probabilities that we associate with these rules to produce the correct parse tree. Or if you're in neural network land, you don't care about the probabilities, you just want to optimize the model's prediction capacity to produce the correct structure. So starting with the kind of more traditional approaches, context-free grammars. I assume everybody has seen a context-free grammar. So we'll go pretty fast, just kind of from your algorithms or compiler class, same thing. We just add a probability, but we have a set of non-terminals. We tend to split them in phrasal categories and part-of-speech categories, just so that we don't need to iterate over all symbols when writing a dynamic program. But in their properties, they're the same. And then we have the words, the terminals, and then a set of rules and a specific start symbol. So if I were to tell you, this is our training data, let's extract the grammar, this would be the grammar that we get. And the rules are normalized such that, or the probabilities are normalized in such a way that, conditioned on the parent, we can sum over the children to get to 1. And so we can take the Penn Treebank corpus as about 1 million words, 40,000 sentences, and extract a grammar of, and then visualize it. And so here is a reduced finite state automaton showing all the ways that a noun phrase can be constructed by taking a determinant, an adjective, and a noun, by combining a determinant and a noun simply. It can be simply a singular or plural noun, and so on and so forth. And if we look at it in detail, there's lots of different ways that things can be combined, and it's a very hairy and messy FSA. So finding the right construction will be challenging in terms of computational complexity, and we will need to be clever about how we organize the computation. So one first important thing when doing dynamic programming for parsing is to binarize the tree or put it in Chomsky normal form. And we'll get to that in a moment, why this is important. But what we'll do is we'll take rules that have more than 2 children, and we will convert them into rules that have 2 children. And we can manipulate the labels in such a way that we can preserve all the information so that it can be exactly reconstructed. Or we can be forgetful and we can omit some information because maybe it's okay to have one prepositional phrase, maybe it's okay to have two, but maybe we want to allow also 3 or 4. And so by binarizing it, we get that flexibility. And the one difference to the full Chomsky normal form is that we won't allow empty constructions or empty elements to keep things simpler. So if we have a binarized grammar, I can give you this simple pseudocode algorithm, and it should give you a parse tree if you're patient. So given a sentence X and indices I to J, a label X, index I to J, and a sentence S, we can compute the best score by saying, okay, if J is equal to I plus 1, so the span is just 1, we can compute the tag score by looking it up in a table. And if the span is larger, we will take the rule, iterate over our rules, and take the best score for the left child and the right child, and multiply them and return that. So a couple questions. Will this work in general? Do you see any problems? Silence. I mean, this is just computing the score. So if I basically, to get the score of the whole sentence, I would say, I want the score of root going from 0 to the sentence length, and here's the sentence. And then you run it, and it recurses and kind of goes and finds everything. We need to explore all the paths. Is that a good or a bad thing? I mean, if you want to find the best tree.
How many paths do you have?
Okay, but how can you save something? Dynamic program. Okay, but maybe more specifically, what do you mean by explore all the paths? Or how would the dynamic programming save you time in exploring all the paths? Yeah.
We are building a stack to find the best score. We are not using the score from the other pre-done scores. That's why I
Okay, but first, is this going to, like, if we had time, like you press start and you go to the beach and then you come back, like, is this going to terminate and compute the right score?
we have assured that there is no
Oh, between the children? Yeah, there's actually, the way it's formulated, there shouldn't be any problem with cycles because we're only doing binary branching, and I didn't specify what this max is over, but I'm splitting it so that K has to be between I and J, right? And so it will take something and break it into something smaller. So eventually you'll hit the base case where you have a span of 1. So it will terminate for sure. Like there's no way to have a cycle with this formulation. So the max is over the rules and over K ranging from I plus 1 to J minus 1. A dependency between a word before K and after K. But the scores, like if it's basically each word affects only the part of speech tag of that word, this X, and then afterwards you just, I mean, when you call this with just over one word, then you're in the base case, so it's factored Okay, so this works, but your point about dynamic programming being better, I agree with, but it's just for efficiency purposes. And maybe to put kind of what was said at the beginning with the different paths, the reason why this is not a great solution is that we'll be recomputing the same units, the same spans. So because this goes top down, when we explore this max here, we make a recursive call. And so just consider the case where like the x, y is the same and just the z changes. We'll make these recursive calls multiple times, even though once we've computed it, we can cache it. And so that's where dynamic programming comes in. And we can say, let's just add these two lines. If we have not computed the score, so we'll store all the scores in a three-dimensional array where we have the label over each span. And if we have not computed it, we'll do the computation that we just did, but then at the end, we're going to store it. And if we have already computed it, then we'll just return it. So this will save us from repeatedly computing the same quantities. The algorithm explores still all combinations, but doesn't repeatedly explore them. And so it will actually terminate much faster than the previous one. But both of them work. So this is memorized top-down parser. It doesn't look at unaries, so you would need to add something here to the max. But you can also do it bottom-up, where you can say, OK, well, let's start populating this chart bottom-up by iterating over all the tags. And we just need to iterate over the position for each word. And then we start building up spans of size 2 going up to n. And then we take I as the starting point and j as the end point. And then we iterate over the rules. And for each split point, k, we try to take the maximum of either the score that we have already computed for this, or the new way that we can generate this symbol x by combining the children y and z, where y and z have these scores. So are the two algorithms equivalent? Do you see any differences? Is one of them faster or to be preferred? Any opinion? I don't know. So the question is, could this explore something that couldn't be produced top-down?
Like eventually you will kill it because it cannot be constructed, but you are computing it and wasting time.
From the top-down. Yes. So when you go top-down, because you don't know what the words are, you're basically running the same algorithm for every sentence. And then you might get to a position where you need to produce a word, but the word is given to you, and you have the wrong part of speech tag, so you've built a parse tree that doesn't actually line up with the sentence below. Yes, that can happen. This one won't do that because it is grounded in the words.
I was just pointing the exact opposite.
Oh, you're pointing the opposite? OK.
Like you could start for English building a constituent of verb phrase at the beginning. Only at top level then you learn that you have nothing that translates both words into verb phrase and something that always needs to be not.
OK, yes. And so this the bottom-up parser has then the opposite problem, that you don't know how things are going to fit together. And so you might take an interpretation of a word that doesn't make sense in the global context. One thing that, like a short sentence that I like to use is, how does a bee fly? Fly is a verb, but when you look at it locally, most part of speech taggers get it wrong because it sees a bee fly, which as a human, you know that maybe there's no such thing as a bee fly. But in terms of a noun phrase, without semantics, just looking at the syntax, it's a perfectly fine noun phrase. And so locally, you might call it a noun phrase, but then you try to combine it with the how, and it just doesn't work. So you need to actually know to use the other interpretation. And so that's why these two things end up being about the same. They will overgenerate certain things that are not compatible with actual sentence, and they'll explore the full space. One thing in practice is that recursive algorithms, if you have a very long sentence, and in theory, sentences, human language, even though you can build infinitely long sentences, people don't do that. The problem is that when you try to analyze the web, there might be sentences where somebody forgot to put punctuation or on purpose just didn't put punctuation, and your sentence splitting algorithm thinks it's one mega long sentence with 1,000 words. And if you get into a recursion that's 1,000 steps deep, then depending on how much memory you have, you can also kind of just run out of memory and crash. So bottom-up algorithms tend to be preferable for that, but you need to just guard for that. Yes? Why is this what? Oh, the score of a rule. It's just the probability that we saw earlier. So, I mean, if you have a probabilistic grammar, it's just this score where we normalize things so that they add up to 1. So the reason we have 0.5 here is because there are two noun phrases, and there are two ways of generating it. So with 50% chance when you're going top down, if you have a noun phrase, you either expand it into this way or into this way. So either as a pronoun or as a determinant and noun. And in practice, you'll have more of these. And we'll see also discriminative grammars where these things are just weights. They're just some numbers, parameters of the model. But for the probabilistic ones, they're probabilities. And so at the end, what I call score here, if it's a probabilistic model, this will be the probability of the tree. So this would be a language model score for how likely is the tree and the sentence, because it's a joint model. So is this relatively clear? Nowadays, some parsers do dynamic programming like this. Many parsers don't. But I think it's a very important building block to know. And so that's why I wanted to cover it in detail. One question I would have here is, what's the asymptotic complexity, the big O complexity? Is it a linear algorithm, quadratic, cubic, n to the fourth, exponential? Somebody's n to the power of 4. Who's giving more? Who's giving less? Or do you want to justify the n to the 4?
I think for the second part of the 4, it's just nesting like 4, 4, 4.
1.
Can go in the worst case, yeah, from 2 to the n.
So this is n.
Yeah.
Then this is n.
Yes.
And then we have two more. So we have four for loops. But this one, is it n or should it be something else? Does it depend on the sentence length? So, OK, this one is not. And then this one is n. Do we care about this one?
No.
Because it's got an additive. So then we have 3 and something for the grammar. So it's O to the n to the third times the grammar constant. And one thing here to keep in mind is that n, when we're dealing with natural sentences and natural language, is going to be on the order of 10, 15, 20, maybe 30, 40 once in a while if you are looking at well-edited newswire text. But in the age of Twitter, n tends to be fairly short, small. And cubic is bad always, but when the n is around 20, it's not that bad. The set of rules can actually be in the hundreds of thousands or even millions. And so the grammar constant in practice tends to be the more important one. And algorithms that try to optimize the speed of this algorithm try to be clever about which rules they iterate over, because certain rules might not be feasible in a local or global context, and keeping track of that either exactly by smart bookkeeping or by doing it in a lossy way and removing certain items can lead to big speedups. So this is the overview. We just did it. The speeds are now a little outdated, but the ballpark is still, I think, the same. OK, I'll skip the unary rules. They're not so important. Well, they're important. They're pain to deal with, but they're details that you can have in the slides and how to keep track of them. So now that we have this basic algorithm, the rest will be more about how do we actually score these parse trees, and kind of these scores that we set up probabilities, how do we manipulate them so that the correct parse structure comes out at the end. And to do that, we have a few things that we can wiggle. We can mess with the set of rules that we have. And we saw that in the kind of conversion to binary. I'll go back. We saw that in the conversion to binary that we can adjust the set of labels and rules, but we can add additional information to these labels if we want. And we'll see a few ways that this was done sort of manually or handcrafted back in the day. And then we'll look at how nowadays with neural network models we can featureize it and basically condition on the input and properties of the input, compute the most likely constituents that we can then put together. But before we go there, one thing I wanted to highlight. So if we look at this algorithm, the reason we have n to the cube is that we can't do anything about these two, right? Like we have to go over all spans from of all sizes and from start to end. But then here we have this split point, which adds a factor of n. And if our rules were not binary, but actually n-ary, so if we had 3 children, what would you need to do? You would need to have not just an index k, but you would have to have an additional index l, because you don't know where the position of each child is. And that would add another n factor, so it would be n to the 4th. And if you have rules that have 4 children, then you would need to iterate over yet another split point. And so in machine translation, sometimes you have no choice, and you have to have these big fragments because your machine translation quality otherwise is not so good. But here, by manipulating the grammar, we can save ourselves from that and keep it cubed. OK. So shortly after the Penn Treebank was released, Eugene Charniak did the obvious thing of taking the corpus, extracting all the rules, and computing the maximum likelihood grammar. And unfortunately, the result was not great, 72%. So F1, do people know what F1 stands for? Anybody? I see a nod. Recall, yes. And so recall and precision, what are they here in this case? And why do we need recall and precision? So precision is of the symbols that your model predicted, how many are correct? And RECO is of the correct symbols in the goal tree, how many did your model predict? Why do we need these two metrics? Because we have unary rules. If we had strictly binary trees, then all the trees would have the same number of symbols. And so your goal tree and your predicted tree would have the same number of symbols, and accuracy would be enough. If you're doing part of speech tagging, you do just accuracy because recall and precision are the same. Here, because we have unaries, one tree can have more than the others. And so if you just focus on precision, then your model would be tempted to never predict a unary because having an extra symbol increases the chance of it being wrong, and therefore you would rather minimize that. If, on the other hand, you focused on recall, then your model would predict unary chains everywhere because you're trying to get all the symbols that are in the goal tree, and you don't know whether there was a unary or not, so let's try to put in a few. There's no penalty for it. And so that's why you do precision and recall. And when you look at the breakdown, most parsers actually are quite well calibrated, and they produce similar precision and recall numbers. But sometimes some systems kind of overpredict or underpredict unaries, and the F1 measure keeps everybody honest. Now, why do you think that this didn't work so well, 72%? Is natural language fully context-free? Probably not, right? Like, what does it mean to be context-free? It means that once you have decided on this noun phrase, everything that is in here is completely independent of the rest of the tree. And that's not quite the case. We're making this approximation for computational reasons, but natural language doesn't quite work like that. And so we need to weaken these independence assumptions in order to model language better. And hopefully, if we model the real phenomena better, we'll also get higher accuracy. And we'll see that this is indeed the case. And then another thing to mention, because it's oftentimes not discussed anymore and just assumed, but given that people have been doing this for more than 20 years, sometimes people forget. This metric, F1 and precision and recall, is great in terms of simplicity and kind of, it's simple to define and simple to explain what you're doing. But is it the right thing in practice? It's debatable. You can have some mistakes that don't matter much. Like you can get the symbol a little bit messed up. You might get kind of singular noun with plural noun confused. Just because I don't have any other symbol here that we can confuse. But these things will matter a lot less than attaching the prepositional phrase in the wrong place where it changes the meaning. And at the same, and yet they will be penalized the same way. And so when you think about how you compare two parsers in practice, this is just a kind of one signal to use, but not the ground truth. There can be systems that have the same performance, but make vastly different types of errors, and therefore the downstream implications can be very different. There can also be inversions where one model appears to be better, but then in practice it actually gets a lot of things wrong. And my example here with the noun was actually something that's also not correct, in that this metric doesn't actually evaluate the part of speech tags. And the reason for that is that part of speech tags are a big fraction of the tree, because every word has a part of speech tag, and then we have logarithmically many afterwards. And they would dominate the metric and make it too easy to get high scores because parsed speech tags are much easier to get right. And so Eugene Charniak said, okay, we're going to do precision and recall on these, the non-terminal nodes that are not parsed speech tags. And we're stuck with that metric. But it makes sense when you're trying to use a parser to actually look at specific constructions that you care about. And so we are doing that internally, and we are also now having a paper in submission where for part of speech tagging, we're saying the average is pretty high, but there are specific cases where nouns and verbs are being confused, and let's focus our attention on these specific cases that are hard and create new data sets that are challenging with respect to specific phenomena, because the average is very easy, but there are tricky cases where we hope that these types of analysis will actually help us reveal the meaning. But if we just look at the average, we might think that we're done. And so that's, I think, something, as you do your research, to keep in mind, don't just blindly optimize the metric, but look under the hood. Why are people doing it that way? And did it make sense 20 years ago when we were at 72%? But we'll see at the end, now we're at 95%. Maybe we want to revisit this assumption and think about other metrics that are more meaningful and capture more accurately what is going on. OK, so as we said, one of the problems with this model is the conditional independence is too strong. So these two noun phrases, I can just take them and swap them. And the score of the tree won't change because it still uses exactly the same constructions. But she heard the noise, and the noise heard she. In terms of language model probability, one of the sentences is grammatical, the other one is not. So you would want the probability for she heard the noise to be much higher than for the noise heard she. And yet this model gives both sentences the same probability, so obviously it's not accurate enough. And so one thing that my advisor, Dan Klein, did when he was a graduate student was to look a little bit more deeply into this and say, OK, if we look at all the noun phrases, here are the probabilities associated with the expansions. So a noun phrase being expanded into another noun phrase in a prepositional phrase 11% of the time, determiner noun 9%, pronoun 6%. But if we look at the context in which this node is, we see that when it's under the S symbol, so it's close to the root of the sentence, it tends to be much more often a prepositional, just a pronoun. And when it is underneath a verb phrase, it is much more often a noun phrase in a prepositional phrase. So what does it mean? Well, when you have a sentence, you're much more likely to use a pronoun, like I did X or he did something. And when it's the object of the verb, there's much more internal structure. Wash the dishes with detergent. And so we want to capture these differences, because if we capture them well, we'll increase the likelihood of the correct sentences. And we can annotate the tree to capture this information. So we can say, OK, it's important to know what the parent is. So we can add a symbol that says, OK, this is a noun phrase underneath a sentence, and this is a noun phrase underneath a verb phrase. Now we have different symbols. And so these two things don't share any statistics anymore. We cannot simply swap them. And we can estimate more accurate probabilities. I'll get to these in a moment. And so you can play kind of grammarian or linguistics and think about all the phenomena that you think are relevant and add them as kind of enrich the symbols. This will create a bigger grammar with more rules, but their probabilities will be more peaked and will give you a tighter fit to the data. Of course, this is very labor intensive, and you also are going to be hitting some limits, because as you introduce more symbols, you'll have fewer examples of each symbol. And so the statistical properties will change, and the probabilities that you will be estimating will be less accurate. And so you need to trade these two things off, because something that might be a plausible thing, if there's not enough data to estimate its properties correctly, might not get you where you want to go. And so in a process of trial and error, Klein and Manning iterated and got it to 86% accuracy. And this was a best paper award at ACL 2003, and a highly influential paper. Lots of people who love linguistics really like this, because it is linguistics really working, and you are bringing in your linguistic intuitions, and it improves the accuracy. But it keeps the model very simple. It's still just a straightforward context-free grammar. If you want to take this and apply it to a new language, you need to start basically from scratch. Some of the intuitions might transfer over, but for new things, for most languages, you would need to adapt it from scratch, and so it's very labor-intensive. Now, instead of annotating top-down the information of the surrounding symbols, one way to really provide like most of the information in a very compact way is to annotate each note with the so-called head word. So the head word is the word that is most important about in a given phrase. So in a noun phrase, this would be one of the nouns, typically the rightmost noun in English. In a verb phrase, this would be the verb. And it preserves most of the information that you need to know. If it's a noun phrase, you don't care about the determiners and adjectives. You want to know that this is a noun phrase for the word noise, and so you might be able to put that in the subject position, but a noun phrase that has the property of the word she shouldn't go here, because heard she is not grammatical. You would say heard her. And this gives you a lot of information, but comes at the expense that you're now really exploding your grammar. If we had, in the Penn Treebank, there are about, I forget what it is, I think it's like 80 different symbols, 40 part-of-speech tags, plus the phrasal categories. And if you annotate each symbol with a lexical item, there's thousands of words. So now you have thousands of symbols. And if you remember the grammar constant and having to loop over all the rules, you have to be clever about how you do that, because if you just loop over all the rules, it will be way too slow. Of course, you know that only certain words are possible. But for example, here, you don't know which word is going to be the head, so you'll need to loop over potentially the words inside the phrase. And so you change the asymptotic complexity. And in terms of the statistical properties, it gets really hard to estimate these probabilities, because you might have seen this noun phrase with that word only once. And so you need to back off to generic noun phrases and mix the probabilities in clever ways. But what this gives you is the ability to differentiate much more accurately between different parse trees. So these two parse trees, if you have no lexicalization and no additional annotation, the children ate the cake with a spoon, they have the same probability according to the context-free grammar, because they use exactly the same set of rules. But obviously, we want to be able to distinguish and not have a tie here. And so we need to add some information, and that can be by lexicalizing the model. And that's what Michael Collins pioneered, and then Eugene Charniak also updated his model to do similar things. And it gets kind of conceptually, it's very simple. Writing the code and getting it to work is actually quite difficult, because you need to annotate every node with a word. Yes?
I have I think a bit of a basic question, but I'm having a hard time understanding how this is very fundamentally different than what we saw yesterday, which was structured for besides the different representation of the problem.
How is this different? I mean, so when people talk about structured prediction, the math tends to be general enough that it captures the trees, but then the examples tend to be sequences only. And so in theory, all the math, I don't know whether Xavier updated his slides, but in general, what he presents, all the math applies here as well. But when you're actually building a model and trying to run the prediction, if you have a sequence model like an HMM or a CRF, the dynamic program is different than what we just saw, the CKY algorithm. Because you only need to label each word with one tag. Here, because we have a hierarchical structure that we're producing, the math carries over, but in practice, when you implement it, the dynamic program will be more complex. Does that make sense?
Yes, I guess the difference more on the algorithmic and not so much on the theory behind it.
Yes. So we'll actually see it very clearly in the second half also. Did you guys cover, you covered probably the structured perceptron, right? So for the structured perceptron, you take your model, you compute on the argmax, and then you check if it's correct, then you move on. If it's not, then you subtract and add. The difference is in the argmax. For sequences, you run one algorithm. For trees, you run a different algorithm. And so because trees are of particular interest in kind of NLP, we have this separate lecture. And that's the main difference. The other thing is also that what works for sequences, basically CRF models, the math carried over, but until a few years ago, computational hardware was just not quite there to run a cubic time algorithm during training. And so we knew how to do it, but we couldn't do it well in practice because nobody had had the time to really fine-tune all the features and things like that. And so now with GPUs and more generic neural network packages, the distinctions are going away slowly. But if you're trying to have sort of the most appropriate model, you will try to exploit the structure of that you're trying to predict to not waste computation. And so these things, like this is really like the lexicalized parse trees, I would say is mostly for like people who want to do parsing research need to be aware of this, I would say. People who want to just do NLP or machine learning more broadly, this is sort of a historical aside of an important paper. You will probably not need to implement anything like that yourself directly. And so, this works much better than the Klein and Manning work. And in fact, even though it predates it, this work, basically, this work came later. It was much worse, and it still got a Best Paper award. So I think this is something important to keep in mind when you start reviewing for conferences, and many of you might already be reviewing for conferences. The accuracy is important, but it's not the only thing that we need to care about. It's very easy to say, oh, this is not state of the art, reject. But there are papers that advance our understanding of how things work, and they might not be getting state of the art accuracy, and that's okay. It's about advancing science and advancing our understanding, and not just about systems engineering and getting the highest number. It's much harder to make that argument, and it requires careful reading and understanding of what the paper is trying to do. But I would say we often, like it goes through sort of this wave where performance goes up, but the systems get way, way complicated. And then somebody comes around and finds a simpler way of doing something. But at the beginning, the accuracy is not quite there yet because the other system has been engineered for many years. And we need to encourage such work because it resets things in a simpler baseline and in a simpler formulation and opens up doors for the future. And so this Klein and Manning work is something that then I built up on for my PhD thesis. And we said, OK, well, taking the intuitions from these lexicalized models, but also the kind of simpler annotations that look at just symbols, can we do this automatically? And can we use clustering of some form to discover more fine-grained distinctions, but do this without having to annotate it by hand? All right, is everybody here familiar with the k-means algorithm? OK, good. So it's basically the same thing, except that instead of clustering points, we are going to compute clusters of these symbols. And to compute these symbols, we'll split each symbol into k subsymbols, and then try to compute the probability of each symbol being part of each cluster. The way that in k-means, you start randomly, and then you compute how likely is each point to come from a cluster centroid, and then you readjust the clusters, and then you iterate. The same way we can do this here by starting randomly, taking each parse tree, and in our minds, splitting it into exponentially many derivations. But in practice, we can do this with simple bookkeeping, where if you remember the CKY algorithm, we had 3 dimensions. We can add a 4th dimension, which is the subindex. And then what this means is that our grammar expands. And we need to figure out how many of these rules do we want, how fine-grained do we want each split to be, and then accordingly compute the parameters for these things, for the rules. And so now we have strictly more flexibility. And instead of optimizing things by hand, where we make a split and then check the probability of the rule and what the parsing accuracy is, we can use the YAM algorithm to learn this. And this was pioneered by Matsuzaki and friends in Japan. And then we at Berkeley picked this idea up and extended it. And for those of you familiar with graphical models, or actually with HMMs and sequence models from yesterday, this algorithm during training is much closer to the sequence case because the structure is given. And so we just need to compute the probability of these latent variables. And we run a modified version of the forward-backward algorithm, compute these probabilities, which then allow us to estimate a grammar. And in terms of parsing accuracy, oops, I think I switched the numbers from the def set to the test set. It's just a little bit better than the Charniak model on the test set. But the main thing is not that it's better, but that it's completely data-driven and therefore can be trained on new languages from scratch without any customization. And so this was a model that was popular, I would say, for 5-6 years, was applied in lots of flavors to different languages and extended. And then with the neural wave has been replaced, but it's what underlies the so-called Berkeley parser that is still used quite a bit as an open source package. So we looked at a few different ways of annotating the symbols. But nowadays, with neural networks, maybe there's more effective ways of doing it. And before we go into the neural network part, one note on generative versus discriminative models. So you've covered both here, I believe. And so you're familiar with generative versus discriminative? Yes? OK. So the models so far that we presented were all generative. So they modeled the joint probability of the tree and the sentence. So this is a slide I made as a grad student and spent a lot of time drawing. So I like to reuse it because it has a lot of animations. So you have the gold tree and the sentence. And you want to increase the probability of both. You don't care about all the other parse trees that are possible for this sentence. You're maximizing the probability of both. And you can do this either with maximum likelihood Or if you have these latent variable grammars, you can do this, again, maximum likelihood algorithm, but EM algorithm because you have latent variables. In discriminative modeling, you want to maximize the conditional likelihood, so the goal tree given the sentence. So at the beginning, the goal tree is one of many possible trees. And what you want is to move the mass from the incorrect trees onto the goal and make the goal tree the most likely one, given the sentence. So the sentence is just something that you condition on. And the hardness here is not in terms of modeling. To your question, the sequence, the structure prediction formulation that Xavier presented covers this very well, and we have known the math for a couple decades. But getting it to actually work in practice was computationally very difficult for a long time. And so people did things like restrict themselves to sentences of length 15 or less. And they showed it on a limited training set of short sentences. Certain models that are discriminative can be better than the generative models, but they couldn't scale it up to the full corpus. And so there was always the question, well, what if you have more data? Does the generative versus discriminative distinction matter in that case, or is the relationship flipped? Because philosophically, there are some people who believe the generative models are the way to go, others that believe that discriminative models are the way to go, and then others who just want to drive up the number and don't care about the formalism so much. So nowadays, with neural networks, we tend to be mostly in the discriminative case, though there is now also more work looking into generative modeling with neural networks, which I think is quite exciting. But we'll now look at a few discriminative models that are first just going to be using features, and then we'll extend the lexical features to be also neural network based. So as I said, we've known the math for a long time. The late Ben Tasker was a lead author of another actually best paper award-winning work at the MNOP 2004. And then it's been refined and extended. So in CRF parsing, we don't care so much about the grammar because we don't want to be restricted by the context-free grammar assumption. As we said, what's around the tree, around a certain phrase does matter when computing the probability of the phrase. And so we want to condition on the entire input and use features of the surrounding words to tell us how likely is, for example, a noun phrase to be spanning the phrase a speech. Well, it depends on what the word before is. So probably when computing this probability, we would want to look at a speech, but also what's before and what's after, and have features over that. And the grammar will only come in when we try to compute a tree that is a valid tree. First, we'll just focus on building models that can score these constituents. So to the question before, the score was the probability under the context-free grammar in the previous cases. Now, we'll just ignore the probabilistic interpretation, and we just say, I want to compute a score of VP versus the score of a noun phrase versus anything else that could go in this slot. And once I have these scores, I will run the CKY algorithm to build the tree that gets the maximum score. And it's the same CKY or Viterbi version of the CKY algorithm as before. But the scores, rather than being constructed bottom-up, they will be just these featurized models that can predict those scores independently. So I'll have features, and these features can be hand-designed, or it can be simply a neural network. And then we will have model parameters that give us the score by taking the dot product between these things. So we can have a sparse part and a dense part, and we can combine the two. And this was proposed by David Hall, and then later refined by Greg Durrett, all at Berkeley. So, and then at the end, we enforce just a tree constraint. So what could these sparse features look like? Well, we'll say that the score of the tree is going to decompose over the score of these units, where R is a partial tree. And so now, rather than scoring a noun phrase going to a noun phrase and prepositional phrase, we're scoring specifically a noun phrase going from position 2 to position 7 and being with a split point of 4 here between the two children. So this unit, and what do we want to use as scores? Well, it's up to us to be creative and take the words that are before, the first word of the phrase, the last word of the phrase, and so on and so forth. And we can play this game to bring in our intuitions the same way that Klein and Manning annotated the tree. But here, because we have a log linear interpretation, we can be much more generous with our features, and we can use regularization to help us overcome statistical stability issues when we don't have enough data. And then on top of that, we can feed the whole set of words as indicator features and use word embeddings and a neural network. So there are different versions of this, of what you can do here. 3 years ago, recurrent models were being used, but I think we didn't have as good of a handle of how to use the representations out of recurrent networks. And so this was a strictly feed-forward model that just looked at the words around the phrase that was being considered. So the word before, the word at the beginning of the phrase, the words around the split point of the children, and at the end, and just after the position. But some words inside the trees were skipped over because the intuition was that they don't matter so much. It's kind of like the head words in the lexicalized case. You don't really care about the red chair. You don't need to model the and red. You want to model chair because for the grammar, that's what matters. And so this was sort of a simplified version of it. And you can do anything, but they did just a feed-forward model and combined it, and were able to get a % improvement over the latent variable model that I presented before. Now, in concurrent work, Oriol Pines and myself and some colleagues at Google were looking at sequence-to-sequence models and said, well, these models seem to work quite well for machine translation, where you're translating from one language to another. What if we interpreted parsing as a sequence-to-sequence problem, where we map from the input sentence to the parse tree? And so this model doesn't know anything about what it's doing in terms of grammar. But if we train it on a bunch of data, maybe it will be able to mimic parsing. And so the paper is called Grammar as a Foreign Language. And we really just took the machine translation model and applied it to a bunch of data. I was very skeptical, and I thought this would never work. I will admit that openly. And I was shocked that it does work. It doesn't work quite as well. When trained only on the Penn Treebank, it gets to 88.6%. So it's below the state of the art. But it's a completely generic model, and it doesn't know anything about the task. So it's impressive that it even remembers to close all these brackets. And in some cases, it didn't. Like in 99% of the cases, it does close them properly. But once in a while, it forgets. And so we had to pad either at the beginning or at the end to just kind of make it a balanced tree. But we tried even nested structures like I have a sister who has a brother, who has a sister, who has a brother, and up to 6 or 7 of these nested clauses, it would remember to close them properly. And LSTMs have since then been shown to be able to do some simple type of counting. And I thought it was very kind of impressive that we were able to learn so much just from a million words. And then to improve the accuracy, what we did is we took a traditional parser, parsed a bunch of data, and then took that data and used it as additional training data, noisy data for this LSTM model. And with that, you can bump up the accuracy to be state-of-the-art. But it's a slightly different scenario because it's learning to imitate also another parser. But it was quite exciting to see this is possible. And I think since then, people have moved beyond just using sequence-to-sequence models, and instead we're plugging directly into the representations of the LSTM and then doing our dynamic programming on top of that. And we'll see that in the dependency parsing case in more detail, and also Chris Dyer probably will talk about that a lot tomorrow. I wanted to just show one new model that is coming up. Oops, there's a T that's extra. It's Kitaev and Klein. It will be presented in a couple of weeks in Australia. So this is brand new work coming out of Berkeley and blowing everybody's mind, I would say, in terms of accuracy. So what they did is they took an encoder, and you can use an LSTM. They're using actually a so-called transformer model with self-attention. I'll kind of talk a little bit more in a second about it. And then what this does is it builds up a representation of the words that is contextualized. So word embeddings give you just a lookup. Given for each word, you have a lookup of the word embedding. When you have an encoder, you run typically a left pass and a right pass with self-attention. It's a bit different, but you're basically building up a representation of the word that is influenced by the words that are around it. And then they're using these representations to compute the scores as in the model that I just showed with the feed-forward structure. So instead of encoding specifically locations around the split points and other things, they just take the representation that they have and do some additional manipulation around the positions, but then feed it into a feed-forward model and produce these probabilities. So this is the chart, the score chart, and then run the CKY algorithm. And to get it to work well, they do global normalization. So it's a CRF model where you compute the probabilities during training, and then you use a max margin objective to maximize it. This is a locally normalized model. This is a globally normalized one. And there's this debate, do you need global normalization or not? We'll see that here it mattered. In the dependency parsing case, I'll show some work where it actually doesn't seem to be necessary. And so this encoder structure, just schematically, it has these 8 layers of attention where they look at the word, the part of speech tag, and the position, and combine them in a transformer architecture. I won't go into the details of what this does, but the exciting thing is that it works really well. 93.6 on the Penn Treebank, just trained on 1 million words. And then if you pre-train the encoder on a bunch of unlabeled text, you can do significantly better. So before we go into the break, just some results. So this is the old slide that I showed 2 years ago. We had been kind of slowly creeping up, and we're around 93. Chris Dyer's work was brand new and was getting to 93.6. And people were trying to distinguish single parsers with models that use additional data from self-training, re-ranking, combination models, all these things. I made a new slide and tried to clean it up. And we have these single model parsers that are just trained on the Penn Treebank without additional data. And then we have things that use either additional data or model combination. And then the first things are linear models. So these are all linear models. And these are linear models. And then these are the darker shades. Oh, actually, darker blue and lighter green. I should flip these. Are neural models. And then the Kitaev and Klein that I just talked about, this is trained on the Penn Treebank, and this is with additional pre-training, but gets to 95%. A couple of things to point out. As I mentioned before, we go through these kind of phases where accuracy increases, and then we come to a new simplified paradigm that opens up doors for improvement. And it's good to take the hit in accuracy because it simplifies the architecture. And you see it on both things, in both settings, that accuracy had improved. We took a hit, but then we improved and we kind of exceeded things. And so here, the same thing. One thing to also note is that a lot of the recent papers don't even cite these old works anymore, even though, for example, Xavier's work was already super accurate in 2008, so 10 years ago. It was beating some of the parsers that were being published in the last couple of years. But somehow people forgot about that work, and they only cited the neural work. So that's another pet peeve of mine, is complaining that people shouldn't forget all the work that came before, because it influenced how people think about these things. Now, final slide. Here are some accuracies on a bunch of different languages for which we have constituency tree banks. And unfortunately, we don't have numbers for this new paper from Nikita Kitaev that is coming up at ACL. But I'm comparing a few different papers from Dan Klein's lab. And you can see the progress. So on average, we moved from 80 to 83 to 85. And who knows, Kitaev might be at 88. So there's definitely progress. The numbers in absolute terms are lower than in English when you look at most of the other languages. And there are a couple of reasons for that. And I'll give you the answers so that you can go for lunch, for breakfast. There are differences in annotation standards. Sometimes a tree bank might have more labels, which makes it harder. And then typically there's less data. So the English tree bank is bigger. That makes the models more accurate. But the last reason might be that some languages are easier to parse and others are harder to parse. But that argument is much harder to make because we're comparing apples to oranges. And I think it tends to be more of an artifact of the fact that people have looked more at English and less at the other languages, and that we have more data. Cool. So with that, enjoy the break, and we'll see each other in half an hour. Or are we doing the photos?
Yes. Guys, we are taking the group photo in the last 10 minutes of the coffee break. Okay? So it's fast.
Hi. Hello, everybody. So welcome back to the second half. We have 1 hour and 20 minutes and a lot to potentially cover. I thought I would skip ahead to one slide before actually kind of starting properly, because I heard some questions to me, and others overheard some other questions about why do we do parsing? Do we need this? And I tried to answer it at the beginning of the lecture, but maybe I'll take a second stab at it. There are multiple potential answers, and I think if you ask different people in the community, you'll get different answers. And also, regarding the importance of parsing going forward. So my personal take on it is sort of hedging in a couple of different directions. So traditionally, what we have done oftentimes in NLP is build these pipeline systems where we extract sentences, do tokenization or segmentation in Chinese where you don't have word boundaries. Then we do part-of-speech tagging, parsing, entity tagging and resolution, and perhaps coreference resolution. And then we try to use this information in downstream tasks. And so we can keep making these components better and more accurate with the hope that they will be useful for downstream tasks. And that's one way that things can go. And these symbolic outputs will never be perfect, but they're fairly easy to digest. They're easy for humans to read. And if you have an engineer working on some type of language understanding system, they can take this module, and it's fairly low-level understanding, but this type of understanding and reasoning can be then used in an application. And if we build it once, we can apply it or use it in different applications. So it scales and modularizes nicely. So you're empowering lots of potential applications by providing these symbolic representations. Of course, there will be errors, and how to recover from those and how to deal with them is going to depend on the application. And so there's also the temptation to bypass it and to just try to train models that go more directly after the task that you care about. And so this slide is from semantic role labeling, but basically you would bypass a lot of the structured analysis and just go from the input to the final prediction that you care about. And if you have a good amount of training data, you can do that. And there can be two sort of philosophically two different ways of doing it. You can just treat it as a sequence tagging task. So Xavier's lecture and everything up till yesterday is still relevant. What we did discuss today with tree structures is less relevant and maybe overkill for many things. In some cases, you might want to have nested structures. And in that case, these parse algorithms, even though you're not using them to produce syntactic parse trees, you're using them to predict some type of other tree structure or graph structure, and therefore the algorithms transfer, but you train them on different data. And so therefore it is useful to continue working on improving these algorithms. And then a third thing that is not shown here is that perhaps the ultimate kind of way forward, and I think a lot of people are hoping that this will be the solution, but I don't think we have very strong results yet in that space, would be that multitask learning and joint learning of multiple tasks and representations is going to be much better than working on specific models for specific tasks. So you could say that you don't need syntax per se, and you don't want to restrict your model to extract only spans from the syntactic parse tree. But instead of discovering phenomena like syntax from raw data, which might be possible but might require a lot of data, you might be able to actually benefit from the Penn Treebank and the linguistic annotation that is there in a multitask setting where the representation that the neural network learns is trained to be good for syntax and for whatever other tasks you care about. And so during training, you do multitask learning, but then you throw away the syntax part. You don't care about the predictions from that part. But because the representation has captured phenomena that are relevant for syntax, it actually gets better at the task that you're trying to do because we think that syntax is general enough and generalizes in this direction. Is that going to be the case? I don't know. But that could be another reason why improving things in this case kind of studying syntax and related algorithms can be useful. And then it can be sort of a joint task where the sharing happens through the hidden layers. It can be in ways that you actually leverage syntax more explicitly, for example, in your attention mechanism, so that instead of having raw attention or self-attention, you attend over some syntactic structure and you get soft input to your system that way. I think Andre and I were talking that next year probably we'll try to revamp and generalize this lecture a little bit more to go beyond syntax and talk explicitly about some of these applications. And I'm doing a little bit with the semantic row labeling at the end of the lecture. But I think we don't really know yet, I would say, what the role of syntax going forward is. And the algorithms are beautiful, so I think it's important to know them, even if you don't use them in your day-to-day life. So, any questions about that or comments? No? All right. Then let's look at dependency parsing. So we saw dependency parser in the first half of the lecture. And so we'll be trying to predict these types of structures. And we'll walk through several algorithms for predicting these structures. Again, similar to the constituency parsing lecture, we'll start with sort of the traditional sparse linear models and move onto the more recent work with neural networks. Okay. The clicker stopped working. So a note on projectivity and non-projectivity. We talked about it at the beginning when we said, what are things that you cannot model with constituencies? Well, crossing arcs are hard to do with constituencies. And actually, when building dependency parsers, this is an important distinction as well, because there will be algorithms that allow you to produce arbitrary graph structures, including graphs where there are crossing arcs. And there will be other algorithms where you won't be able to produce crossing arcs. Depending on the language, this might or might not be a big deal. Typically, you would want the crossing arcs, because even in English, there can be annotation schemes and sentences where it can be helpful. For example, temporal modifiers tend to be fairly free word order in English. And so John saw a dog yesterday, which was a Yorkshire Terrier. You would end up with this crossing arc. And if you want to restrict yourself to projective trees, you would need to figure out what to do with this arc. In free word order languages like Czech, there are going to be a lot of these arcs. And so it's important for your algorithm to be able to produce them. Formal definitions of dependency graph for completeness. You want the graph structure to be connected without cycles, and each word can have only one head. The converse is not true. Each word can have multiple modifiers. And so kind of the red chair, the and red both have chair as their head, but chair has both of them as modifiers. And then this is the formal condition for projective parse trees. If you draw it on a planar piece of paper and there are no ways to avoid crossing the arcs, then you have a non-projective parse tree. At a high level, there are two styles of dependency parsing, and I think this distinction is perhaps getting a little bit more blurry nowadays, but I would still think that it makes sense to divide it this way. And they have different trade-offs. So transition-based parsers consume a sentence from left to right and try to build up a parse structure along the way. They tend to be fast and linear time. but use beam search perhaps to preserve some ambiguity. Graph-based structures, on the other hand, evaluate all potential arcs and can use dynamic programming for doing that, tend to be a little bit slower. Now, in terms of accuracy, I think it's a constant battle. It keeps on going back and forth, which one is the most accurate today. But sort of to an approximation, greedy transition-based parsers tend to be very, very fast because they don't need to score that many arcs. Once you add a beam, things can get significantly slower. And one thing here, again, thinking about the first part of the lecture where we had the cubic times CKY algorithm, if your k in the beam size, basically the number of hypotheses that you maintain for ambiguity is big, like 64, and your sentence is of 15 words, then this k is actually quite important. So focusing on just the asymptotic complexity can be misleading. In constituency parsing, it was the grammar constant that kind of gets hidden, but it's really important. Here, the beam size doesn't show up in the asymptotic consideration, but actually does matter quite a bit in practice. And one other thing that's interesting is for graph-based parsing, thanks to clever bookkeeping, first order and second order parsers are asymptotically both cubic, but the speed differences because of the complexity of the search space is definitely there. And then once you go to third order, it becomes n to the fourth, so you need to do some type of pruning. And we'll talk about non-projectivity and projectivity in the context of the Beagle notation as well, because anything beyond first order, actually for non-projective parsing, is NP-complete, while first order parsing is, for non-projective models, is actually more efficient than n to the cubed. So we'll start with the simplest models, where we'll just look at each arc in isolation and try to score it. And it's going to be very similar to the constituency parsing case, where we started with simple models, added more and more complexity, and then moved on to neural networks and were able to get rid of a lot of the structure that was imposed and just use the modeling power and capacity of the neural networks to score more accurately the basic units that allow us to combine, that we can use to combine the tree. And so here, similarly, we'll start with arc-factored models. We'll then build up to richer structures. And then we'll look at what neural network models are doing, and in many cases, actually simplifying this again and just having richer ways of scoring the arcs and using continuous representations that are context sensitive to model the things that were modeled traditionally with features. So this is exactly the same formulation as what you've seen so far with structured prediction in Xavier's notes. So we are going to factor the tree into a set of individual arcs. And if we have a way of scoring the individual arcs, we just need to combine them. Now the question is this accurate? And obviously, the same way that context-free grammars were not fully adequate to model the properties of language, an arc-factored model is not going to be sufficient. For example, in an arc-factored model, you evaluate each arc independently. So it is perfectly fine to have multiple subjects for a given verb, because there's no constraint that you can impose to say, oh, you cannot have two subjects on this verb because you're scoring each independently. And if it's a noun close to the verb, that looks like a good subject. And there might be another one that you score in the same way. And so getting these types of global constraints into the model would require a higher order factorization. Cool. So Now let's look at how we can build up these parse trees, because if you, assuming you can score each of the args, you then need to figure out how do I put this together into a structure that covers the whole sentence with a maximal score. And one way to visualize this is to say, let's build a matrix and kind of two-dimensional array, and we'll index it by the sentence positions, and we'll have the heads and the modifiers, and we'll have an additional dedicated symbol for the root. And we'll try to, we can put the score of each of these. Each cell will score the arc from the head to the modifier. And we can then try to find the best tree. So they're going to be n squared arcs that we need to score, and then we need to put them together. So kind of just to introduce the notation, this would be the best parse tree for this particular, or the correct parse tree for this particular case, where you have the visualization up there and then the matrix notation down here. You can then think about how to organize your computation to get this the best tree. So we can do this bottom up, similar to the way that we were doing constituency parsing, by taking partial trees and reasoning about the heads of those trees and attaching one to the other to form a larger partial tree. So I'll be drawing these, or they're traditionally drawn with these triangles. And so you can have one partial parse tree going from I to j with a head word h, be built out either from multiple subtrees that all modify the same head, or you can have you can try to group it so that you only have one child either to the left or to the right. And this is, again, somewhat analogous to the binarization trick, where if we don't binarize, we have to loop over many indices, and it makes our computation go up asymptotically. But if we organize our computation in the right way, we can make things more efficient. And so the idea will be to fill up the chart bottom up, where for now just assume we have these weights for each edge, and we'll use them to compute the scores of the entire tree structure. We'll talk about where they come from. Typically, in dependency parsing, I would say most of the time we actually use discriminative models, so these are just going to be weights rather than generative models where these would be probabilities. Tends to not work as well. And so if we were to just say we'll build up parse trees by combining small partial structures, and we can take adjacent trees that have been built up and then introduce an arc either in this direction or in the other direction, we'll need to maximize over a total of 5 indices. So where are the 5 indices coming from? In the constituency parse tree case, we had the start index, the size of the span, and the split point. We have the same things here, but additionally, for each span, we have to maintain an index for the head, because we don't know where the head inside the span is. It can theoretically be any of these positions. And so when maximizing, we would need to maximize over these as well. And this is exactly the same as in the lexicalized parser case, where we would need to maintain these two additional indices, so we end up with n to the fifth. And n to the fifth is prohibitive. Even with modern hardware, this would be very painful. So people thought about this for a while, and Jason Eisner, who has been a lecturer here as well, proposed an algorithm in '96 that is nowadays oftentimes referred to as the Eisner algorithm. And the idea was to be kind of smart about how you organize your bottom-up computation, and to impose some restrictions on the structures or the order in which you build up the structures, which doesn't result in any restriction on the final parse tree, but allows you to get rid of these H and H prime indices that would be needed in order to keep track of the head. So if you say that we'll have these triangles that instead of having the head anywhere in the span, they'll be required to have the head either on the left end or on the right end of the span, then we can come up with an algorithm where we do the bottom-up process in a two-stage way. So we'll have complete items where the head is on one of the edges, and those are shown as triangles. And then we have incomplete items that we store temporarily, and that can be combined with complete items to form another complete item. And those are shown as trapezoids. And so if we have something like this, where we have two complete items, so this structure has its head at index h, this one has it at head at h prime, we can combine these two, producing a head here, and then we can, in the next step, attach this green structure to the blue to form a complete one. So we can look at this in practice on an example, and then we'll look at the pseudocode as well. So the operators that you have are just these, as well as the mirror ones. So we can do it in combine things in the other direction as well. And we start with a structure where each position is initialized with basically a self arc or an empty arc, and we'll try to build up larger structures. Also, to give credit where credit is due, Sasha Rush, who was noticed at the as a thank you at the beginning of the slide, he actually drew these slides for a conference talk when we worked together, and he'll be giving a talk later as well. So what we do here is we start with an empty chart and these minimal triangles. And in the first step, if you recall, we can take triangles that are facing each other and combine them to trapezoids. And we can take afterwards trapezoids and attach triangles to them to complete them to make them triangles again. So what would be the first step? Well, we have, potentially we can combine any pair, but in order to build up the goal tree, we know what arcs we would want, so we will take these ones and put them together. And now we have some trapezoids, and so the next thing would be to extend it and slurp the stuff over, and then we go to the next larger arcs and build up these consecutively larger units, iterating between trapezoids and triangles. In terms of pseudocode, it's very straightforward. We have a data structure that has now a few more dimensions, but kind of should remind you of what we have seen already. So we have the start and the end index, and then we actually will have a direction and an indicator whether this is a complete or an incomplete item. So the last two dimensions are binary, and the first two are indices. This is for unlabeled parsing. If we wanted to add labels, we can either do it jointly or we can label the arcs afterwards. Kind of different trade-offs. And so we initialize everything with 0, And then we start by iterating first over the complete items to create incomplete items. So we take these complete items, indicated by 1, and check for arrows that are facing each other. And the score becomes the score of these partial constituents that we have so far, plus the score of the arc going in one direction versus going in the other direction. And that's indicated here, the directionality. And so this is a bottom-up search we're doing, trying to compute the maximum score. So we're maximizing over these. And then once we have these incomplete items, we try to join them with adjacent items that are complete, and there's no new arcs being introduced. We're just doing this for bookkeeping, and we compute these scores. And so at the end, at the top, you'll have the maximum scoring arc factor tree, and then you need to look at the arc max to find out and trace back where it came from using the Viterbi algorithm. So if you have a way to score the arcs, can you build up a parse tree for a dependency parser? Yeah? Good. I don't know what the labs are this year, but in the past, you would have, you might have to do this. So it's good to ask questions if it's unclear. So one question, is this going to produce non-projective or projective trees? Projective. Anybody who thinks it can also do non-projective? No. It's the same basic units and argumentation as in the constituency case. We're doing it slightly differently because we're doing dependency arcs, but we're combining only adjacent things. And so this will be projective. And it will be, in terms of complexity, and to the cube, because we have to iterate over the same 3 kind of types of indices as before. So we have these 2 for loops, and then the third one is hidden in this max here. So I didn't write out the max. Now, we'll look, before we look at how these things are scored, actually, the scoring, one very simple way that you can learn weights for this type of model, and then actually produces very, very good performance, is to just use the structure perceptron. So you start with a vector of zeros. So your arc score will be all zeros. And then you need to define what are the features that you want. So you can just have a feature that looks at the 2 words, and you just keep basically a hash table of all pairs of words that you've seen, and you then, with the structured perceptron, learn feature weights. But in practice, you want to go beyond these features and look at more interesting features. And so you want a log linear formulation potentially, where you take a dot product between a feature vector and your model weights. So the word identities are good features, but they're going to be sparse, because in a new sentence, you might encounter words that you haven't seen together in the same sentence, and so scoring them will give you a 0 score. So you want to have something that you can back off from. And part of speech tags are a very powerful signal. So knowing whether something is a noun or a verb will tell you oftentimes what relationship these 2 words are in. And then you can extract features also just from one side. You can just say, oh, this is a verb, and I don't care what's on the other side. It's always going to be the head or something like that. The model might learn. And one thing here to note is the part of speech tags conceptually could be incorporated into the parsing algorithm and could be part of the search that you conduct. But in practice, for dependency parsing, we assume that we have run a part of speech tagger and we use them then as discrete features in the model. While for constituency parsing, people typically do dynamic programming over the part of speech tags as well. With neural network models for dependency parsing, some people use the part of speech tags as features, and some don't. Actually, the constituency parsing model that I showed, the final one, the Kitaev et al. Model, uses part of speech tags as explicit features from a separate model, breaking with the tradition of constituency parsers doing joint search. While the dependency parsing models that I'll show here by Timothy Dozat and all actually use sometimes part of speech tags, but also work quite well without them. And so this is just something to keep in mind. In the past, people spent a lot of time figuring out what features to use. And this is the set of features that a state-of-the-art first-order parser would extract from each arc. So you can see how extensive this list is, because it looks at the word itself, the part of speech tag, the two words, the part of speech tags of both words, the part of speech tags of adjacent words, of things in between, the distance, the direction, and so on and so forth. And it seems fairly clear that even though this is the parameters are set in a data-driven way, there's a lot of manual tuning that goes into this, and it would be nice to replace that with something that's automatically learned. And neural networks give us a way to do that. So we'll see how it's done. But for many years, this is what people did, and people would inherit the feature sets from other parsers and extend them with new ones. Andre Martins just got out. When he built a third-order parser, he came up with some novel features that he incorporated in his model. And so you would always develop a model and figure out how to train it. But in addition to that, people would tweak the features that they use. And so if you have a way to extract these features, then you can simply do transition-based parsing, structured perceptron training by scoring each the parse tree using the dynamic program that I showed before, and then comparing whether it matches the goal, and if not, adjusting your parameter weights and iterating. Typically, you would then, on top of that, do averaging at the end. That works better than taking the final weight vector, but the procedure is basically the same. So I think this is roughly what you'll need to implement a feature extractor and then use the features in a model for prediction. Now, beyond arc-factored projective parsing, we can also look at non-projective parsing. And it turns out that those theoretical computer science algorithms classes that you take as an undergrad are useful in NLP as well. Because non-projective parsing can be viewed as finding the maximum spanning tree in a directed graph. And you can leverage all the beautiful algorithms that you have from your algorithms classes. So, of course, we won't have necessarily, actually, so if we have unlabeled parsing, we'll have scores for arcs, and in theory, this will be a fully connected graph, but maybe we can prune some arcs. For example, there won't be, the root can only be the head, it cannot be a modifier. So there will be one node that has a special status. If we want to do labeled parsing, we could have multiple arcs between the nodes and have the label be the distinguishing factor. But let's for now focus on just unlabeled parsing. So we'll have directionality on the arcs. So there will be between two nodes, we can have arcs in both directions. And we're trying to find the maximum spanning tree, which visits every node and produces a fully connected graph. We can pre-compute all the scores for each arc, given some features and a weight vector. And we'll still be using the structured perceptron to learn the weights. So the arc, in the structured perceptron, it doesn't matter how you produce the arc max. You can do it with the dynamic program, or you can do it with the maximum spanning tree. You can still use the same algorithm for optimizing the weights, but you'll produce different types of structures and models at the end. So assuming you have weights so that you can score each arc, we can build a graph and have scores on the edges. And now we would like to find the maximum spanning tree. And there's an algorithm called Chu-Liu-Edmonds. Do people remember maximum spanning tree algorithms from algorithms class? Anybody? Okay, some people. It's one of those beautiful and simple algorithms where the greedy solution turns out to be the globally best solution, which is sadly not always the case, or usually not the case. So the way that it works is that we will start by looking at the incoming edges into each vertex, and we'll find the highest scoring incoming edge. So if we look at the word saw, we have an incoming edge from John with score 20, one from Ruth with score 10, and one from Mary with score 0. So it's the 21 is the high scoring one. Then if we look at Ruth, there's nothing incoming. If we look at John, the highest incoming one, so it's 9 here, 30 here, 11 here, so it's 30. So we have John to saw and saw to John. And then for Mary, we have 30, 9, and 3, it's 30. So it's this substructure, this cycle between John and saw, and then Mary. If you have a cycle, unfortunately, you're not done. If we had no cycle, we would be done and we would have a maximum spanning. If we have no cycles and we have a fully connected tree, we would be done. But now we have a cycle and actually a disconnected node. What we have is this. So this doesn't look too good. So we need to do actually a modification. And the modification on the graph is, or an operation on the graph, is to take the cycle. It can span multiple nodes. It doesn't have to be just a pair. But we can take the cycle and then contract it by keeping the highest scoring Oops, this is not showing. By contracting it as one node and then recalculating the arc weights to adjust for this new structure. So if we look at the original one, we contract it. We need to contract this part, so we create one mega node here. And then we adjust the weights for the incoming arcs. So the incoming arc from root was 10, and we'll take the maximum, the 30, and so it will become 40. And this edge from Mary to John, we'll connect it with the 20, so it becomes 11 plus 20, 31. And the other ones stay as they are, 9 and 30. And so now finding the maximum spanning, the maximum incoming edge here will give us 40 into the big node, and then 30 into Mary. And so at that point, we will be done, and we can reconstruct the final edge. So we have the final tree would be this one with then the edge reconstructed. So the algorithm to write down takes a little bit more time, but intuitively, you just iterate between finding the highest incoming arc, keeping track of those, checking whether you have a tree. If you don't, contracting the cycles and repeating. And implementing it is a little bit more hairy, and implementing it efficiently is even more hairy, but luckily it's a standard algorithm, so there are plenty of implementations around it. Cool. Any questions about the maximum spanning tree version? So this doesn't keep track of non-projectivity and will therefore produce non-projective arcs. The interesting thing is that the projective version we can extend fairly easily to higher order factorizations, where we don't keep track of just each individual arc, but we can keep track of multiple arcs. And we just need to extend the size of the chart that we keep track of. For the maximum spanning tree version, higher order factorizations are NP complete to compute. So unfortunately, we need to resort to approximate solutions for those. Cool. So now let's switch gears and look into transition-based parsing. So transition-based parsing, as I said, is a different way of thinking about it, the problem, and we'll be building up the parse tree incrementally left to right, and we'll use a stack to keep track of intermediate data structures. There are different transition strategies. Arc standard, arc eager are the two sort of most commonly used strategies. Joachim Nievre has this very nice extended paper in the Computational Linguistics Journal that discusses a lot of the pros and cons and the variations, and new strategies have also been suggested, like hybrid ones. But just to walk you through the basic idea is that you start with an empty stack and all the words on the buffer, and you want to put things together into a parse tree. The constraints that are listed here are that the beginning, the stack is empty and everything is on the buffer. At the end, we have the root symbol on the stack and a parse tree structure underneath. Here's the parse tree structure actually. And then an empty buffer. And we'll have these operators shift, which moves the top item from the buffer onto the stack. And then left arc and right arc, potentially with a label, where we take the top items on the stack and introduce an arc between them. So either from I to J, and then J is left over as the only item, or from J to I, in which case I is left over as the top item. And then we keep track of the parse tree that we've built. So let's walk through this. At the beginning, we have no choice but to push things onto the stack. We still cannot introduce any arcs because we have only one item on the stack, so we have to move one more item over. Now we actually have a choice. We can either push more things onto the stack or combine the first two items either in one direction or in the other. And it turns out that the right thing to do is to introduce a left arc with a subject label, and then we shift more, shift again, introduce another arc, and so on and so forth, until we have produced the final parse tree. So how does this thing operate? Well, it's actually just a simple classifier. And given a stack and buffer configuration, we can extract features and score the different options. So the labels of the classifier are the action that it's going to take. And we can treat it actually as a greedy classification problem where we ignore completely the fact that this is a structured prediction case, and we just train classifiers greedily. You can train an SVM or a maximum entropy model or a neural network classifier on these individual observations. Given a buffer and a stack, what's the right action to take? And then you string them together. This will suffer from the label bias problem that you might have seen in earlier lectures. And so what works oftentimes better is to do globally normalized training and basically complete the full sentence and only do the update at the end while maintaining a beam. But these are kind of different options that you have. In practice, you get back into this game of designing features, looking at the words and the part of speech tags and words that are in the vicinity. Back in the day, you used to just have to do a lot of kind of handcrafted features, and the rest of the machinery was fairly easy. You had some regularization and some loss function, but when you have just structured perceptron or an SVM, it's, there are not that many things to fiddle with. Most of the energy went into designing the features, and this is the feature model for a state-of-the-art sparse linear feature kind of model that doesn't use a neural network representation. And it seems very clear, again, as we saw for the graph-based models, that if you have to design something like this by hand, it's unlikely that you'll find the optimal features by hand. And a neural network might be a much better way to learn what the right features are and the right combinations. And so that's actually what Dan-Chi Chen and Chris Manning proposed now 4 years ago. Seems obvious in hindsight, but was quite novel back then. And they said, let's keep the transition-based framework, and instead of going all the way to sequence and trying to kind of predict the entire tree in one go with neural networks, let's use the tools that have been developed for kind of hand-tuned features and combine them with the benefits of the representations that neural networks can learn, but still control what the neural network does. And so what they said is we can take just feature locators around the words between we are trying to make a decision for, and embed those words, the part of speech tags, the potential labels of arc trees, of arcs that have already been built, and put this in a feed-forward model. And then the softmax is going to be over the different decisions, shift, left arc, right arc. And this basically allows us to get rid of the entire hand-engineered feature set and makes it fairly easy to just generate training instances for neural network that we can train independently of the transition system. And then once we have this neural network, we can combine it with the transition system. And as we process the sentence, it can help us make the decisions and parse. And this was surprisingly effective. I think it was eye-opening to people how much headroom there was. And subsequently, together with some colleagues at Google, we extended this work to kind of be a little smarter about how we allocate the dimensions in the hidden layer, making the hidden layers bigger, adding more hidden layers, and then adding global training either with the structured perceptron or with a CRF. And so in the following, I'll show some of the results of these modifications. But one thing that we discovered along the way was also that when you have neural network models, there are potentially a lot more knobs that you can turn. And simply re-implementing somebody else's work might not get you the right results. So you need to be very careful about the batch sizes and the loss function and all these lower level details that are oftentimes not described in a paper. But sometimes, if you do them very carefully, you can actually get even better results than the original paper. So when we were trying to replicate the results, we ended up with something that was slightly better, actually, in terms of accuracy. But to just kind of show you a few of the differences, or kind of the variance that you can get. This is simply from a plot showing the development set and, well, actually two different development sets, a development set and a tuning set. So these are two different sections of the Penn tree bank. And the unlabeled accuracy for different models evaluated on both things for different model sizes. So one hidden layer of size 200, and then two hidden layers of size 200, as well as pre-trained word embeddings and not pre-trained word embeddings. So if you just ran once from a random seed, you might get different conclusions than if you run a lot of different random seeds and choose systematically what model you select. So this is one thing that I think nowadays most people are familiar with and know, but when you're running experiments, I would encourage you, it costs extra time to run multiple experiments in parallel, but you will save time down the road from making wrong conclusions if you evaluate multiple runs, because otherwise you might just get randomly lucky in a particular configuration, but miss out on a better configuration. And then the other thing why I wanted to show this slide is the importance of not overfitting to the test set and the importance of having separate held out sets that you don't optimize your performance on explicitly. Because we have a training and a test set so that the test set is blind and the model doesn't set its parameters to the test set, because otherwise we would be just memorizing, right? Like we want the model to generalize. Now, if you train multiple models and you pick the best one on the test set, it's unlikely that it's going to generalize to to completely unseen sentences, because you optimized it on the test set. So that's why we typically have a def set and then a test set, and we try to pick the best model on the def set, but then when we evaluate, we just run it once on the test set and we compare different models on the test set so that they are compared fairly. When you run multiple experiments, you might be tempted to compare the def and the test set, and I would really strongly encourage you to not do that. Ideally, each test set should be used only once ever. In practice, that's impossible. So we reuse test sets, but we're going to fool ourselves if we implicitly tune things on the test set that the performance is going to be like that on real data. And so at best, like the best thing would be to run only once on the test set per paper that you write. In practice, you might run twice or three times because you have camera ready and before camera ready and I don't know what. But please don't run on the test set all the time, because you'll get artificially high numbers, but then when you try to run this model in practice, it won't work as well. And so here, when we plot on the separate tune and def sets, you can see that there are models that tend to, like overall there's a trend along the diagonal. Models that do better on one tend to do better on the other, but if you're optimizing on the def set, you would choose from these models without the pre-training, you would choose this one. It's the highest one on the def set. But if you then take this model and run it on a test set, it's quite likely that it's overfitting to the def set, because it's somewhat of an outlier compared to this range. If, on the other hand, you take the best thing from the tune set, you choose this one, you would lose 0.4 on the def set, but you would end up somewhere in the middle of the pack, and it's quite likely that you would get comparable performance on the test set because you haven't overfit. And one nice thing with this plot here is that these models down here, the variance is quite big, so you can get lucky and get pretty good performance. But as we make the model more powerful, we make it bigger, and we add pre-training so that we converge to a good local optimum. We see that the correlation between the tune and the def set actually increases, and the range is a bit smaller. It's still not perfect. There are a couple outliers down here. But overall, any one of these models up here would be fine. And so using the tuning set for tuning, we would select this model, which is not the maximum on the def set, but it's pretty close. And we're comfortable proceeding and know that it will be hopefully performing reasonably well on the test set as well. OK. So now switching gears a little bit, or a lot. Actually, before we go there, I'll show you these results. So these are this is the slide I showed 2 years ago. I have new numbers now from more recent work. But just to compare, just to show you where we are. So these are linear models, a graph-based model, third order, and a transition-based model that we're getting about 93% unlabeled accuracy score or 91 labeled score. Then Chen and Manning came with this work that was 92. And as I said, again, we saw a drop compared to the state of the art, but it was a much simpler model and opened up the door for more progress. So when we try to re-implement it, just keeping the dimensions the same, but using HGD and maybe slightly different nonlinearities, we were able to get quite a bit better performance. Otherwise, everything was the same. And then adding a deeper neural network using perceptron for beam search. So these are greedy. This has a beam search. And then doing semi-supervised learning. We also have a version with a CRF. We were able to get to close to 95% at the end. Chris Dyer, at the same time, had this DEC LSTM model. He was here at the beginning. He'll be talking tomorrow about his recurrent models and might mention this. Was within the same rough range. Now, since then, we have had another, I would say, sort of phase shift where we have simplified the models again. And we're now at the point where you might ask, well, do we need parsing or can we bypass it? But in a way, the model has become very simple and somewhat agnostic to the task. And we'll see that similar types of models work for both parsing and semantic row labeling. And I think this kind of confirms this idea that I was pitching to you at the beginning, saying that the algorithms that we develop in the parsing context or in the tree prediction space are useful and generalized beyond pure syntax. So what Timothy Dozat proposed last year was to just run a bi-LSTM. So run an LSTM in one direction and another one in the other direction, and then take the representations of each word. So there's ... The sentence is basically here. So there's the root, and it's part of speech tag, and period, and it's part of speech tag. And in between, we have all the words in the part of speech tags. And we feed them through an LSTM layer in one direction, LSTM in the other direction. And then we'll take these representations on the top, and we'll generate a head representation and a dependent representation. So trying to model this phrase being the head versus this model being the dependent. And then we can feed them into what they call biaffine self-attention layer. So we want to score all pairs of arcs, of heads and potential modifiers. And we'll use these representations and do SGD through the entire network to adjust the embeddings to produce high scores for the correct parse trees. So basically, the way that you can think about it is that instead of having attention in the machine translation case where you translate from one sentence to another, you're doing self-attention, so the same sentence on both sides, and you're trying to see for each word what are words that have a high weight and high importance, so that the representation is a weighted average of the words in the sentence that it attends to. And then you actually, I should say here, then you combine them with a maximum spanning tree algorithm at inference time. So this model is actually trained on the goat without taking into account any alternative structures and without enforcing any global constraints. But because it's trained on coherent data, it actually learns reasonable representations so that then you can score each arc independently and then just combine them with a maximum spanning tree algorithm. So you can use either the non-projective version, or you can use the projective Eisner algorithm and just use this, instead of having the linear scores, you use this factorization with the neural network to produce the scores. So the algorithm is still the same, but how you produce the scores has changed. And the results are impressively good. We're now comfortably into the 95% accuracy. And even on the labels, which tend to be quite a bit harder, we're approaching 9. So this is the Timothy Dozat work. This is a different transition-based parser that we haven't talked about. But yeah, we're in the 94% range. And so in both constituency parsing and dependency parsing now for English, we are above 95%. I think if you had asked the community a couple of years ago whether this is possible, I think many people would have said it's not possible, or at least not anytime soon. There are no hard statistics on what the inter-annotator agreement is, but rule of thumb tends to suggest that it's somewhere around 97%. And so there's not much headroom left because humans make mistakes themselves on this task. And when we look at multilingual results, this is from the Connell shared task last year. Here are the results for a few different systems. Timothy Dozat's parser did the best, 81% on average, and then a few other systems. Looking at all tree banks versus large tree banks versus, this is a separate set of tree banks where the same sentences were annotated, translated and annotated in different languages and small ones. You can see some variations, and you can see in general this trend that I mentioned. Larger tree banks are easier to parse than smaller tree banks. But yeah, the nice thing about this setup is that we have more than 30 tree banks, and they're all in the same format, and so it's easy to build one model and try it out on a bunch of different data. When reporting numbers, you end up with way too many numbers, so here they're shown in aggregate, but you can drill down into it and see what is going on for the different systems. Cool, so we have 15 minutes, and I was going to switch to some semantic role labeling and talk about other structures that are related to meaning. But before we go there, any questions about dependency parsing or constituency parsing? No? Yes? Yep. Yeah. Yeah, so the question is, are there things that decode directly into a tree structure? I don't, I mean, it depends on how you want to see things. So you can linearize, like, what does it mean to decode in a tree structure, right? Like you need to do it in some type of sequence. Okay, I mean, so the parsing model, the last one for the constituency parsing that I showed, the Kitaev et al., it scores all the nodes, and then we just use the CKY algorithm to find the best tree, because you want to find the globally best one rather than a greedy one. But if you use that in a greedy way, maybe that could be viewed like that. I think when you have exhaustive search, it's because the structure is not fixed. It's not just a labeling problem. I think it's hard to not have the dynamic programming component. You need, if you're going greedy, then you can have a tree structured decoder. Does that make sense? And so what you have is sometimes you have tree structured encoders. So there are tree LSTMs that try to consume a sentence not in a linear order, but in a tree. But on the decoding side, unless you go greedy, I think you will always have to score potentially competing constituents, and then you need some form of reconciling the whole thing. So that's why I think you end up bypassing a lot of the more traditional machinery for enforcing the constraints. So you can score each piece individually, but then at the end you do want to have a tree, and you need to figure out which pieces to use of the ones that you have scored. And we'll see that here actually in the semantic row labeling quite explicitly. So semantic row labeling, the idea is that parse trees are nice for linguists, but you pick up a random person on the street, they can speak a language, but most likely they won't be able to draw exactly a Penn Treebank style tree, because there's a lot of convention that has gone into the annotations. And so some people might say, well, that level of detail is maybe overkill. Maybe we need some just higher level abstraction. And so semantic rows are one form of abstraction that is perhaps more intuitive to read. So for each predicate, for each verb approximation, like you can also have non-predicates, but let's say only verbs are predicates. What we care about are the arguments of the verb, because those are typically the events that happen. And so you have an agent, which is the subject, and then you can have multiple objects that are the patients. And then you can have additional optional arguments like time or place. And so one way to reveal the semantics of or kind of the meaning of a sentence is to annotate it with these things and say, okay, there's a temporal modifier on January 13, 2018, and then issued is the verb, and something is being issued. So it's the patient, and the agent is actually not specified in this particular first sentence. Because we don't know who did the issuing. But then in the second sentence, there's the alert stated that there was an incoming ballistic missile. So the alert is the agent of this new predicate stated. And it also refers back to this other alert, and is connected via coreference, and so on and so forth. And traditionally, this was done, as I was showing in the slide, by first doing part-of-speech tagging, parsing, detecting entities, and then using the units from the parse tree as the arguments in these representations. So these would be constituents or subtrees in the dependency or constituency tree. And for many years, people believed that the best way to do this, or empirically it was also shown, that the best way to get these structures was to do first syntactic analysis, find these meaningful units, and then try to put them together in this higher order representation. But lately, people have tried to just bypass the whole thing and say, well, can we just do this as a sequence tagging problem where we ignore these hierarchical structures and we'll just say, we're going to label each word with a tag, and we'll have begin, inside, outside, as well as a label. So this will be argument 0, beginning of the argument 0, which is the agent 0 or the agent argument, meaning the subject. This is inside. This is then the beginning of the verb. And then this is the beginning of argument 1, the patient, and then some modifiers, and so on and so forth. And so you can then take this and aggregate it to spans by saying, okay, well, actually, this is the argument 0, this is the verb argument 1, and then we have this additional modifier. If you were to take an HMM or CRF and run this, it would work very badly. That's why nobody was doing it, and that's why people used to take the parse tree and then extract the information based on the parse tree, because you need some global constraints, and you need to have information from further down in the sentence to make a decision about the argument and what function this word plays in the global sentence. But with an LSTM or any type of recurrent encoder, the encoder has access to the full sentence, and it can build up a continuous representation for this particular word that models things that are on the left and things that are on the right. And so you know you can get better information about what role this word is playing in the global context. So what Lu Heng He and colleagues at University of Washington did was to say, okay, let's build a generic encoder, and then we'll have decoders on top of that, and we will try to use a shared representation for all the different arguments. And additionally, we will also model multiple potential verbs. So if you have multiple verbs, you can have one predicate argument structure or one frame for this verb. You have an arg0 for this verb and an arg1. And then for this other verb, you can have different arg0s and arg1s. Oops, there should be one. And then when we train the model, we have the gold supervision. When we test, we'll give the sentence, and we'll give an additional indicator of which word, which verb we're trying to get the predictions for. So the model is very simple. It's a bi-LSTM, and then you can just try to do directly a prediction. And this works okay. It's not great, and you can certainly do better. And so what Lu Heng then suggests to do on top of that is to construct all potential spans as represented by the representation from this right to left and left to right and right to left LSTMs. And so you can get n-squared spans potentially, which would be very expensive, and you need to score them all. But then they do beam pruning and reduce it to a fixed set of spans, and they also limit the length of the span. So if you have a very long sentence, they will say, we don't tolerate spans beyond a certain length, and then use those with a local classifier to combine them, and then label directly the spans rather than the individual BIO tags as was proposed before. And so the way this works is, actually the linear numbers are missing, the linear model numbers, unfortunately I don't have them here. But comparing the bio stuff is called, so you have the, we don't have the numbers here, I need to add them for completeness, but you have these types of models that use the deep BioLSTM and then biosequence, and then deep SRL is this model that produces not a biosequence over individual words, but over the spans, and then decodes with those, and bypasses the entire, both of these bypass the parse trees, and achieve improvements of more than 5% absolute over the pipeline systems. And when you look at the deep SRL thing, the baseline, then then building an ensemble, and then adding pre-trained word representations that are context sensitive, you can improve quite significantly. The linear numbers are, the linear model numbers are in the high 70s, I think. So we have a similar story as in parsing, where we had plateaued with linear models, and then there was a dip when we went to neural, but then things have progressed tremendously in the last couple of years. How are these algorithms being used? I think hopefully some of the evening talks will shed some light on either the algorithms or the outputs of these systems and how they're being used. And I'm happy to chat more afterwards as well about how things are done at Google. So with this, we have 1 minute left. Any questions? Yes, Joe.
So the parsing, interesting thing is that the transition-based, the grid parsing, and the graph-based parsing, which are very, very different, end up having a very similar accuracy.
Yes.
And I wonder if you look at the what kind of examples or what kind of constituents or the mistakes each of those makes, do they differ or do they actually end up with a very, very similar solution as well?
Yeah, so the question was for dependency parsing, we have very different approaches to end up with roughly the same accuracy. I don't think anybody has looked at it very recently. Ryan McDonald and Joachim Nivre have a paper from a few years ago where they compared it for linear models. And there again, they were at roughly the same accuracy. And they found that the transition-based models are much better at the short arcs that are close by, and the graph, but then they fall off, while the graph models tend to be a little worse on the close arcs, but are better on the long distance arcs, which I think makes sense. And so then they proposed an ensemble method that worked better than both. And so I suspect it's still roughly the same type of thing, but there's also not that much headroom left. So I think we're getting more and more of these things right. But I think it's also, I think we're getting to the point where we need to go beyond the aggregate, the average number of arcs that we get right. And so internally at Google, we have created challenge sets just for prepositional phrases and conjunctions, things that really are close to the meaning of what's going on in a sentence. And accuracies there are in the 70s and 80s. So there's a lot of headroom on those. But they just play a small role in the average, so we need to have focused data sets. An interesting thing for those things is that actually humans are very good at labeling those, even though they don't know the formalism. They know whether you're eating pasta with a fork or with tomato sauce. They understand intuitively that these things play a different role. Yeah?
So maybe I didn't quite understand that, but let's say the cache drawer is computed with some
Okay, so it varies. So the question is, how do we train just like small components that score edges, or do we do inference and then backpropagate through all decisions? And so that's, I think, the difference between the locally kind of normalized models. So in the transition-based work, you can have a locally normalized model where you just extract atomic classification decisions from your training data, just the gold data, and you train a classifier on those, and then you use that at prediction time, and it will be used in sequence, but it was never trained in sequence. And so it works okay when it's greedy, but once you introduce a beam, you don't get much of a benefit from the beam. So in order to get the beam to work better, what at least we have found, but I think, I don't know, Cho might agree or not agree, is we found that you need to do global normalization. So you need to actually run inference during training time with a beam, and then at the end backpropagate through all the decisions so that you overcome the label bias problem and you don't get stuck in a path that looks locally very good, and you learn to discriminate these things more globally. And so some models will do backpropagation through everything, and others will just train on individual decisions. And some people believe that once you have an LSTM representation layer on the bottom, that distinction matters less because you get a lot of the global context through your LSTM. But then you're locally normalizing, but you're backpropagating through everything. So you're kind of, that hard distinction that I was trying to make before doesn't exist as much anymore.
One second. Let's work for the speaker repeating the question.
So a little bit more conceptual question with like the application of the syntax. So what do you think about like, for example, models like the work of Saucher, where you try to use syntax as a guide for the compositional semantics? So like try to compose using syntax explicitly, or I guess in more recent models, more implicitly through attention or something like that, if this is a possible application of syntax?
Yes, definitely. I mean, we use sometimes syntax internally directly. So information extraction systems will use it. Some of the machine translation systems still use it. In text-to-speech, it is useful to know what grammatical role something plays. But more and more it's being used indirectly as a side signal. And so you can imagine various ways of doing that by feeding your model not just the raw text, but some additional annotations, or having a multitask set up during training. And therefore, so basically, I think there's this conceptually this interesting thing. When you have multiple tasks or annotations, you can try to add them as input to the model, and then you have an explicit representation. Or you can train a multitask model that tries to predict the things that you could also have as annotations. And if you put them as an output, you're hoping that then the hidden layers will learn the properties that are important for that. And then at test time, you don't need to supply them and you're not so dependent. I think it's more elegant, but it's a little harder to actually get to work. Cool. Well, thank you all for the attention, and enjoy lunch.